Okay, so welcome. In this lecture, we are going to talk about using the Laplace transform to solve second order IVPs. So on here, I have written sort of a list of the Laplace transforms and their inverse transforms, some of which we just covered in the last video, but these are things you'll sort of need to know. Specifically, we're going to want to focus at least on these few, which are sort of new. Okay. So let's start by looking at the first example. So we're going to solve the following initial value problem. Or you know what, let's actually make that 7, just because sometimes my 5s look like S's. And we're going to use the Laplace transform. All right, now this is a pretty straightforward problem that we could sort of solve via other means, but I'm just going to introduce the Laplace transform because, as it turns out, for a certain set of problems we're going to look at a later lecture, Laplace transform is really just a great way of going about doing it. But okay, so what we do, right? We take the Laplace transform of both sides. All right, so again, we're going to use sort of this notation, capital Y, or sometimes capital Y of S is the Laplace transform of Y. And so we can split this up using the linearity property. And we haven't necessarily discussed it explicitly, but if you think about it for a minute in terms of the integral, the Laplace transform of 0 still has to be 0. All right, now I'm sure sort of what you're thinking is, what is the Laplace transform of y double prime? Well, we should remember we have a formula already for Laplace transform of the derivative. More specifically, the Laplace transform for the derivative of any function is s times the Laplace transform of f of t minus f of 0. So using this, we see that the Laplace transform of y prime, right, is s times y minus y of 0. And using that y double prime is just y prime prime, right? We can see that the Laplace transform of y double prime is s times the Laplace transform of y prime minus y prime of 0. All right, and now we just sort of nest it. We use this formula right here, so we have s times s capital Y minus y of 0 minus y prime of 0. So this is sort of our general formula for the second derivative. So let's go ahead and plug that in and use our specific values. So bringing this sort of all the way down here. We have this as s squared times y minus s times y of 0, which is 1. Minus y double prime. I'm sorry, y prime of 0, which is 7. Plus 9 times y equals 0. Right, so remember, this was my y, this is the Laplace transform of y double prime. And then we have 9 times the Laplace transform of y. Okay. So now we can just go ahead and try to solve for y. Okay, so we can see that capital Y is equal to s plus 7 over s squared plus 9. And now when we can't really factor the bottom here, so what we want to rely on are the formulas for the Laplace transform of cosine and the Laplace transform of sine. So in this case, right, we have our A is 9, so we should be looking for something of the form 3 s squared plus 9 and s over s squared plus 9. So we'll split it up once more, s over s squared plus 9 plus 7/3 times 3 over s squared plus 9. And this is necessary because looking back up, right, this is the Laplace transform of sine of 3t. So now we take the inverse Laplace transform. Looking at our table, we can identify that. And that. So we get that our solution is this, which be Laplace, inverse Laplace transform of that, which is cosine of 3t, and then plus 7/3 inverse Laplace transform of 3 over s squared plus 9, which is sine of 3t. And that would be our final answer. All right. So sort of note the key formula that we used here, or really sort of the following pattern. So, right, if we just say that the Laplace transform of little y is capital Y, then the Laplace transform of y prime is s times y minus y evaluated at 0. The Laplace transform of y double prime is s times this minus y0 minus y prime evaluated at 0. And just rewriting that with some simplification, s squared times y minus s times y0 minus y prime of 0. And just to do one more, y Laplace transform of the third derivative of y is again s times the Laplace transform of y double prime minus y double prime of 0. And if we went ahead and actually simplified that out, we would get s cubed times y minus s squared times little y evaluated at 0 minus s times y prime evaluated at 0 minus y double prime of 0. And sort of this sort of pattern increases. So if I have the Laplace transform, of the nth derivative of y, that's going to be s to the nth power times y minus s to the n minus first power times y of 0, all the way down, minus s y prime of 0. I'm sorry, Sn minus second derivative evaluated at 0 minus y n minus first evaluated at 0. So there's a general pattern here. I could say I highly doubt we're going to use anything past this point, and 98% of the time we're just going to be using the second derivative. All right, let's look at one more. Okay, so we're going to look at something slightly more complicated because I want to point something out. So still very straightforward. We could definitely solve this without Laplace transform. However, let's still use Laplace transform. Let's switch color. Okay, so here we're going to have s squared times y minus s times y of 0 minus y prime of 0 minus 4 times s capital Y minus y of 0, and then plus 5. Oh, whoops, I forgot the y there. There we go. Okay, so now we want to plug in our different values. So s squared minus s times negative 3 minus 0 minus 4sy minus negative 3 plus 5y. Forgot my capital Y here. And we can go ahead, we want to combine all of the terms. Okay, so I want to sort of note just sort of one little thing you can do to check. This here, this coefficient of the capital Y, should always be essentially the characteristic polynomial of your starting complementary equation. Right, so s squared y double prime minus 4s minus 4y prime plus 5 plus 5y. Okay, so moving everything over to the other side, y equals minus 3s plus 12 all over s squared minus 4s plus 5. All right. So now again, we want to do a Laplace transform. And here's sort of what I want to point out. Or, sorry, not a Laplace transform, a partial fraction decomposition. So we cannot factor this denominator, but we can rewrite it like this. So if we complete the square, we get s minus 2 squared plus 1. Anytime you're doing a Laplace transform and you sort of can't factor it, and more explicitly, like if it has imaginary roots. So if you do that, this is what you want to do. You want to complete the square. So doing that, we sort of want to note two things. Right, we had this formula that says we had formulas for Laplace transform of cosine, for sine, and we had the shift formula. And just to, I guess, mix it up, we'll use b's here. So from these, if we combine these, we can see that the Laplace transform of e to the at times cosine of bt is s minus a all over s minus a squared plus b squared. Similarly, if I instead multiply by sine, then what I get is b over s minus a squared plus b squared. Okay. So here's the point I want to make. So this is sort of a non-standard partial fraction decomposition because, we have no real roots. So instead what we're going to do is write it like this. We have a, and now here's sort of the trick. I want to write it like s minus a. That way, at the end, we know what we're going to end up with in terms of the Laplace transform. Here, you could multiply by b, but I'm going to not. I'm just going to try to remember at the end to divide by b when I take the inverse transform. All right. So again, we sort of multiply through. We'll get negative 3s plus 12 equals a. Oh, that should not be a, that should be 2. Times s minus 2 plus b. Right, so now what this says is negative 3s plus 12 equals as minus 2a plus b. So from the coefficients of s, we see that a has to be negative 3, and then 12 equals b minus 2a, or 2 times 3, and so we get b equals 18. Okay, plugging that back in, we have that capital Y is negative 3 times s minus 2 plus 18 over s minus 2 squared plus 1. So now we're taking the inverse Laplace transform. Remember here, we don't actually have to put, I guess, in this case, this is a bad example to bring up b because b is 1. So we can just really pull out that 18. We get -3. Remember what this means. It means we have cosine, or an e to the 2t times our cosine of t. And then plus 18 times e to the 2t sine of t. And that is going to be our final answer. Okay, I'm going to do one more. I'm not going to fully work this one through, but I'll work it through up to the partial fraction decomposition. All right, so again, we take the Laplace transform of both sides. So here I'm just going to plug them in. So minus s times y of 0, which is 1. And then minus y prime of 0, which is -5. So just using colors to show where those numbers are coming from. S times y plus 11, s times y minus, again, y of 0. All right, so continuing through, we should get s squared plus 11s minus 26 times y, and then minus s plus 5 minus 1 . Note here we can again check that this coefficient of capital Y is the same as the complementary or the characteristic polynomial of the equation, and we see that it is. And if I move that over to the other side and sort of do some simplification, and if I note that this is factors, as 26 is 2 times 13, and right, has to be positive 13, so I get positive 11. I get y equals s squared plus 4s plus 18 all over s minus 2 now squared times s plus 13. All right, so here I would do partial fraction decomposition. Let me remind you how that exactly looked. I have a double root here, so I want to include a second power of s minus 2 squared and a factor for just s minus 2. And I would sort of go ahead and get, if I, actually do the partial fraction decomposition, I get that a is 2, so 2 over s minus 2 squared, plus 2/5, 1 over s minus 2, and plus 3/5, 1 over s plus 13. Transforming this back again, I see that this is 2, and then I have 1 over s minus a squared, so that's going to be t, but with a shift by e to the 2t, plus 2/5 e to the 2t plus 3/5 e to the negative 13t. Right. So now just to end it with an exercise, so solve the following. Again, use the Laplace transform. I realize this is pretty easy and you could solve it, any of the methods we learned in the last, but we're going to look at some in the next lecture that you can still sort of use, but it actually becomes very, very complicated to use our previous techniques, and Laplace transforms much easier. So just think of this as practice. Okay, so give that a shot. All right, and you should have gotten by the end, after you do your partial fraction decomposition, for capital Y, you have 3 over s plus 1 plus 5 over s squared plus 4. And now, we note and here's one little thing. Remember, the formula for sine, I have to have that the numerator is the square root of this constant term. So I have to bring out a 5/2 and leave a 2 in there. And this would give me my final answer of 3 e to the negative t plus 5/2 sine of 2t. All right.